All right. The other thing I wanted to mention in terms of entropy that I think I got wrong the other day, it's not wrong, but it's jumping all over the place. What is wrong with this thing? Okay. What does that stand for? Standard. Okay, that stands for standard entropy of formation. And of course we have, whoops, not S naught, we have H naught F, which is the standard enthalpy of formation. And we're going to learn another one today, which is G naught F, which is standard Gibbs free energy of formation. Do you remember how last day I said nothing actually has an entropy of 0 because nothing is at 0 Kelvin? Okay, that is true, but, and the reason I said that is because when we use the formulas, so we have all these three things and we use them all in these formulas where we have delta G naught of reaction is equal to sum of what? Yep. Yes, I want you to tell your partner what the other half of that is. And if you're playing on your phone, get off your phone. Hold on. What's delta H naught of reaction equal to? Mm-hmm. Yeah. Now, I want you to look at this. What's different about the equation when we're using entropy? Yes. Yes. We're not saying what is the entropy of formation, we're just saying what is the entropy. It probably won't matter to you on the test because they're going to give you the actual values. They'll give you the delta H naught of formations that you need. They will give you the delta G naughts of formations that you need. And they will give you S naught of those things that you need. Yes? So they're not going to be like, but what it comes down to is last day I told you that S naught is not going to be 0, which is true, but delta S naught of formation of an element is 0. Because the change in enthalpy to make an element, the change in anything, hang on, let's go back to where we were. So any delta G naught F, delta H naught F, and delta S naught F for an element in its what? Standard state. How do we know it's in its standard state? Okay, and you know most elements' standard states, yes? What is the standard state for aluminum? What's the standard state for oxygen? What is the standard state for lithium? What's the standard state for mercury? Okay, so all of those are just like that. And for carbon, carbon is a weird one. They consider it to be graphite, okay? Because there are several solid forms of carbon. Graphite is considered to be the standard state for carbon. Okay? Now, any G naught, F, all of these things of formation for an element in the standard state equals what? 0. Is good? Okay. Now, the S values that you will be given are not S formation. They're not delta S of formation. So you will have elements, they're S naught of formation, they're just S naught will not be 0 because it's not how much entropy is changed when they are made. Yes? I don't know why. Yeah. Talk to your second year chemistry professor in physical chemistry. Physical chemistry was not my friend. In fact, physical chemistry, as far as I know, was nobody's friend. My husband said of physical chemistry, he's like, yeah, that was non-trivial. Okay, great. Right? My dad, who did his major in physics, said he didn't understand it the first time through. My husband didn't understand it until he was like in 4th year. And I was a biochemist, so I was like, just set that aside, keep moving. Okay. All right. Now, let's go to we were looking at quantifying entropy. So S, we got to, this is page 11. So this is where I said S naught of an element at standard state does not equal 0. So I'm going to write in here, but delta S naught formation of an element at standard state equals 0 is good. But our formula does not use delta and formation. It just uses S naught. Is good? Okay, cool. So we got through there. We did some calculation with that. That part's pretty straightforward. The nice thing about thermochemistry in this exam is that most of it just involves finding the correct formula and plugging things in. It doesn't actually involve truly having a deep understanding, which is a relief, because I will not be the one who will be able to give that to you, okay? You'll probably need to do some calculus and stuff before you truly understand it. I don't know. All right, we talked about all the different degrees of freedom of water. Let's just keep moving then. Okay, and now we are moving on to page 16. Page 16. A few years ago, I've been teaching this for years, and I keep trying to understand things better so I can explain them better to my students. I watched a video on Gibbs free energy to see if it would be a good learning tool for my students. I will quote the first couple lines here. What is Gibbs free energy? Well, we don't really know. Okay, like literally, this is people who are experts in this, and they're like, we don't really know. The moral being, don't really try to understand it, not unless you're getting your PhD in physical chemistry. Okay, and then, like, more power to you. Okay? Rather, what you need to be able to do is you need to be able to write a definition. So let's look at the definition. It is a state function that relates enthalpy and entropy. That's it. You need to know the symbol for it. Okay, Gibbs free energy is G. If we put a naught after it, what does this little naught mean? At standard state. Okay, when we put a delta G, it's a change in Gibbs free energy. Delta G naught, change in Gibbs free energy at standard state. We will most often be using this one, okay? So the other ones you can just kind of put aside and just worry about this one. So we need to know what its definition is. What does it mean that it's a state function? Tell your partner, what does it mean that it is a state function? Doesn't matter how you get from A to B, it's just the change in the two, okay? What is it useful for? That's what we need to know is, what is it useful for? It is useful for predicting the spontaneity. In other words, the new language, thermodynamic favorability of a reaction. And it can tell you the position of an equilibrium. So if delta G naught is less than 0, what does that tell you if it's less than 0? It is If something is less than 0, it is negative. So if you have a negative delta G, then K is going to be greater than 1, which means you have more products than reactants. Yes? That's just a statement of fact. So if delta G is negative, K is greater than 1, products are favored. If delta G is greater than 0, in other words, if delta G is positive, then the reactants are favored at equilibrium and K is less than 1. Is good? Okay. I'm sorry I'm so grumpy today. I think it's just because I can't talk. That's making me like grumpy. Like, nah. Anyway. Everyone in my family is grumpy right now. My husband's grumpy right now. I'm grumpy right now. We're just a big grumpy old family. So I think we need to get over it at some point. So I'm going to try and get over it. Oh, here we go. All right. If we are at standard state, and delta G is negative, if delta G is less than 0, the forward reaction is thermodynamically favored. If delta G is greater than 0, in other words, if it is positive, the forward reaction is thermodynamically unfavored. Is this sounding like kind of like what we did with entropy and enthalpy? Yeah, so now we're just going to be putting numbers in rather than just saying, oh, entropy favors this side, enthalpy favors this side, and where we go, we're actually going to put numbers in and say, where does it actually lie, okay? And the final thing you need to be able to do with delta G is you need to be able to do calculations with it. All of these formulas are given on your golden sheet. Let's go take a look at our golden sheet. So it's going to be towards the second page. So here are our delta G reactions. There's another one, but we won't get to this until unit 6. Okay, so that one we're going to take in place in unit 6. That's to do with the, what do you call it? The electrochemical cells, okay, or cell potential, galvanic cell potential. Woohoo! Okay. So, look at this. Delta G is equal to delta H minus temperature times delta S. So delta G is basically saying if you have a positive delta H and you have a negative delta S, what happens if delta S is negative? What happens to this term if delta S is negative? It becomes positive. So if delta H is positive and delta S is negative, then you have positive and positive, and you have delta G is going to be positive. And what do you remember about a positive delta G? It's thermodynamically unfavorable. The reactants are favored. And if you think about that, if delta H is positive, yes, and if delta S is negative, it means we're becoming less random. Yes, I'm going to keep using the word random. If the energy is less dispersed, okay, if it's becoming less random, that is less favored, right? So everything is favoring the reactants, okay? And I mean, we can go through each of the different cases, but that's in general how it works, okay? So it combines those two terms. Now, the higher the temperature, the more the entropy matters. Yes, the more the entropy term matters. because, of course, you get more motion and stuff out of that. Okay, back to here. We go. All right, so in this worksheet, we're going to focus on delta G naught is equal to delta H naught minus T delta S naught. And one thing you should realize is that delta G is usually given in kilojoules per mole. Delta H is usually given in kilojoules per mole. And delta S, is usually given in joules per mole Kelvin. So these are the given units. Make your life annoying, because I think the reason is because it gives you reasonable size numbers for each of them. Okay. However, what it does mean is that if you're working with this formula, you need to make sure all your units are the same before you start adding and subtracting. It usually involves taking delta S and converting it to kilojoules. Okay, so you have to watch out for your units because they're usually different. Now let's remember, if delta G is negative, what can you say about the reaction? It is well, that was sad. Thermodynamically favored. If delta G is positive, what can you say about the reaction? Thermodynamically unfavored. Okay. So this should be reviewed, this part here. A decrease in enthalpy will drive a reaction forward. An increase in entropy will drive a reaction forward. So let's look at all the different conditions. According to delta G equals delta H minus T delta S, if we have a negative delta H and a positive S, what will you end up with? If delta H is negative and delta S is positive, delta G must be negative. Are we good with why that is? Yes? Okay. Both terms are going to be negative. I mean, I show you like the whole walking it through. Here we have a negative delta H and a positive delta S, and this negative makes it negative, right? And so overall it's negative. So that's going to be thermodynamically favored. All right, let's look and see if we have an endothermic reaction. If delta H is positive and entropy decreases, both terms in the equation will be, so if we have positive delta H and we have negative delta S, what is Gibbs free energy going to be? Delta G will always be positive. And what does that tell you? Not thermodynamically favored. I'm just going to call it thiodine favored. Okay. In both of the above cases, you don't actually have to calculate the value of delta G to tell if it's spontaneous. Favored, thermodynamically favored, or thermodynamically non-favored, unfavored. You don't have to calculate. Ooh, good question for you. How is it possible for a spontaneous reaction not proceed? It is thermodynamically favorable, but you put the reactants together and they just sit there and nothing happens. Yeah, the activation energy is very high. Even though something may be favored thermodynamically, if the activation energy is too high, it just can't get started. If it gets started, it will go and go and go and go and go, but it just might not be able to get going. So this is burning. Yes? So that there's burning, and you can see you end up with more gas molecules. And we produce heat. So for example, a spark. Yes? Is good? We say it's not kinetically favored. It can be thermodynamically favored, but it's not, the kinetics are not conducive to a reaction. He's good? Yeah? Okay. What if the driving forces oppose each other? Hi. Back here. Hi, Joel. Whenever you have time. Why did you guys not tell me this thing is like all askew? That would drive me crazy. Oy, oy, oy. It's still really small. You guys are too funny. It's straight to you because you're on that side. That's awesome. Okay. So if the driving forces oppose one another, what's happening? Everybody's on their phones. Why is everybody on their phones today? What's happening?
I didn't know what definition for were.
That's okay. I'm just wondering why, like I'm looking around and I'm like, there's a ton of people on their phones, and I'm just wondering what's going on today in particular. Is there something special? Nothing special. Okay. If you're on your phone because you're looking up a definition of word, that's fine. You guys don't have to put your phones up there because you're grown-ups now, almost, right? You're like close to grown-ups, right? So manage it. If you're using it to help you with chemistry, if you're using it as your calculator, if you're looking up a word, those would be appropriate uses of your phone during class. If you are just on your phone doing stuff, then that's not an appropriate use of your phone during class, okay? Okay, temperature. Temperature will determine whether delta G is positive or negative. If the temperature is large, big, then the T delta S term will dominate and determine the spontaneity. If the temperature is small, then the delta H term will dominate and determine spontaneity because the T delta S term will be small. Is good? Yes. Okay, so let's say we have exothermic, so delta H is negative, and we have entropy is decreasing, so delta S is negative. So now we have a negative and a positive, yes. It's going to depend on whether, if T is big, the positive will dominate. Yes. Yeah, it applies the same way the other way around. Okay, so you would actually need to take the numbers given to you in the question and plug them in and calculate it. Okay, so it's not actually any more difficult other than the fact that you need to be able to do a bit of easy math. Yeah? Okay. How are we doing? This is just going over example after example. Oh, do we need to go through all of those? Are we good? We're good? Okay. Oh, and look, there's exercises. Yeah. So, how are you guys doing with all of your equilibrium review? I have to be honest with you guys, like usually equilibrium quizzes are really poorly done by regular classes. So if you're looking at your mark and you're like, oh my God, it sucked, like nobody failed it. You know what I mean? And in the regular class, failing is it happens regularly because you get lots of people who it's kind of rare in here to have people not use race tables. And I know if it happened to you, it's okay. You now know, and you won't make that same mistake on your test. Whereas in my regular class, I can use a race table 17,000 times on every quiz and every test, and they still don't use a race table, and I want to weep. Because I'm like, use a goddamn race table. Sorry. No. Okay. I need to become well so I'm not grumpy and not potty mouthed. Okay, so that would be helpful. Do you have time this evening to do some of the questions for 2.6a and 2.6b? Is that a no? Okay, study for your equilibrium test, okay? Just go study for your equilibrium test.